Hi folks, this is my Whirlpool 40-gallon residential water heater, and I was just checking it the other day and I noticed that it was installed back in April of 2012, and I found my original receipt. Apparently I paid about $488 for this unit that I bought from the local Lowe's store, and I installed it myself. It hasn't been touched since it was installed, and in fact I'm kind of breaking my cardinal rule that don't fix what ain't broke, but we're getting on to 11 years of use now, and having not been drained, cleaned, or any maintenance work done on it, I'm long overdue, because the owner's manual says that, first of all, you should check, I believe within about the first 3 years, you should check the condition of the anode rods, and then every year after that, you should check them again. Well, I'm a little overdue for that, but I think most of us probably don't follow that rule, because, hey, it's a lot of fun to take these anodes out. In fact, I've had some tools here that I will show you that I tried to use. I started out with this 3/4 inch drive, 24-inch breakover bar, and takes a 1 1/16 fitting. I put that on there and put a 2x4 between my discharge pipes and attempted to move it, and well, frankly, nothing happened. I could have put an extension on that. I'm not too worried about breaking a 3/4 inch drive breakover bar, but it was obviously in there really, really tight. My recommendation is to use an impact tool to remove this. This is a pneumatic, this is Central Pneumatics impact wrench. It's something I use on my automobiles. So the only bad thing about this, I had to drag down my small portable air compressor, hook up a pneumatic line, and this is a 1/2 inch drive, so I installed this on the top of it and pulled the trigger. At first, really nothing happened, but I kept trying, and eventually I saw it move just a tiny bit, and then suddenly it did break loose. It's a whole lot less effort. I have seen some people take these anodes out using an electrically driven 1/2 inch drive impact tools, such as the ones that Harbor Freight sells. But anyway, I think the impact tool is probably the way to go. I'm not going to say I couldn't have gotten it out just using a breakover bar with extensions, but it was really hard. Now, this unit is equipped actually with 2 anode rods, and I only removed one of them, and after, well, approximately 11 years, this is the rod I removed. I believe this is a standard magnesium rod, and frankly, it's in surprisingly good condition. But I had other plans, so I went ahead and removed it, and anyway, this is what you see. And in place of that, this anode, I have installed an electrically powered anode. This is a Chinese-made product. I think I gave about $80 for it. If you look around on eBay, you can find these. But basically, rather than using magnesium, you have a small electrical power supply, and you shouldn't have to worry about the deterioration of the anode with age, because the this anode begins to be sacrificed. As you can see, the white material on here, the anode is sacrificed, and I can see some places where this has definitely been sacrificed and gone into solution, but slowly over time. If you see some of these really old water heaters, sometimes most of these have like a steel rod right down the center with the magnesium attached to the outside, and sometimes there's nothing left except parts and pieces of the steel rod. And so this one is much better shaped than that. But anyway, possibly your question might be, okay, so you're going to an electrically driven anode. What's it going to cost to operate it? Well, the literature says that this unit will draw 1.5 watts. So 1.5 watts operating 24 hours a day times 365 days a year is, if I've punched my calculator right here, that's about 13,000 kilowatt hours. Well, no, 13,000 watt hours, or 13.1 kilowatt hours. All right, so 13.1, and my utility around here is about between 14 and 14.5 cents. Let's say it's 14.5 cents per kilowatt. So I'll multiply that times 0.14. Well, it would help if I get the right number. 145. So operating cost is going to be about $1.90 a year. More expensive than using anodes, but at the same time I don't have to go in here every year and try to check to see what the condition of the anodes are to make sure that my tank is not going to rust out. And the installation technique, basically, I think this shows the picture. You can't see much now because I already have it in here, but you have a top stainless steel fitting and about a 6-inch long rod. It came in this box actually, and that rod is made out of titanium. I think that's a fairly noble metal, so it doesn't deteriorate with the electron flow through it. And in this particular case, for some reason there was a box here that originally had a time clock in it when we purchased the house. The time clock was never used, and I just here a few years ago put in a power meter so I could keep an eye on how many kilowatts of power is consumed by this water heater. And so I just tapped in. There was also a neutral pulled in here, and the neutral is not needed by the water heater, but it was available. So I came out here, put a 120 volt socket extended out to, just used a piece of Romex here, hooked it up, and this is now my receptacle that powers up the little power supply that goes to the unit. Now you purists are going to say, you've got a heavy duty power supply here. Yes, it's a number 10 30 amp circuit, and you're hooking a 20 amp rated device to it. Yeah, but this thing only draws an amp and a half, or a 1.5 watts, so you know it doesn't even know it's connected. And this is dedicated to just to operate this unit. It's not intended for a general purpose receptacle. Now I could have hooked this up to 240 volts because this little power supply, at least with this one, will operate on it from anywhere from 100 volts AC to 240 volts. So I could have just if the neutral hadn't been available, I could have hooked it up to 240 volts. The only reason I didn't was I was always concerned that if I didn't have it carefully labeled, somebody would come in and plug 120 volts on this, and if I had it hooked up for 240, why, it could end up damaging some equipment. As I took this anode out, I suspended it just with my hand down in through the hole in the tank, and then used my current meter to measure how much current was being generated by this existing anode, and I came up with 0.8 milliamps. Now this morning I have hooked my meter directly into the circuit from the power supply, and now I turn it on. You can see it's running just a little over. This is set for 20 milliamps maximum current. So this is reading 5.08 right at this instant. Milliamps of current that's being produced by this new powered electrode that's been installed. And I don't know if you can see my hand, but it actually inserts into the top of the tank right where my fingers are located now. So there's more than 5 times as much current being produced at this moment, at least, as compared to the original anode. I know that that's probably good. The more current, probably the more protection. So I'm assuming that if this old anode was doing its job and is producing a 0.8 milliamps, and I'm now running 5 milliamps, it should offer superior protection from corrosion. Today the project is to try to remove some of the deposits, the calcium deposits that I believe have accumulated into the bottom of this tank as a result of, say, 11 years of operation. Usually what happens is the calcium products, first they collect on the hot heating elements, and as the elements expand and contract, then it causes the calcium to flake and fall to the bottom. So over the years you get a buildup starting from the very bottom of the tank, and sometimes, in my experience, you can get enough deposits in here that it actually builds up till it covers the lower element, which is located behind this plate. If that happens, you run some risk of that element, because it's insulated by the solid material, the calcium deposits that have built up. It'll overheat and burn out. So most of the time, the first element to fail on your electric heater is the lower one. And I'm going to try a gadget that this is new to me. I don't know how it's going to work out. It's called the Turbo Tank Cleaner. And basically what you do is take the valve out. It's a 3/4 inch fitting. You slide this into the tank and connect the electric drill to the back of it, and this wails around inside the tank. These solids have a tendency to kind of congeal into a very weak. They're not like concrete, but they are stuck together. It beats them up, and supposedly it pulls these solids in. It's got a little grinding mechanism here in the base of it. It comes out as a slurry. As you're running water through the tank, it comes out through this fitting. You hook a hose in, and we'll run that hose outside. So this will be an adventure to see if this really works. I have cleaned these tanks before manually by taking out a heating element and trying to fish solids out through the hole where the heating element goes in, but it's a real bear. So I'm hoping that this may allow me to remove solids from the tank without having to completely remove the tank and take it out of the building. had a hose discharging into a 5-gallon bucket here, and pour some of the water off here so we can get a feel for the material that was taken out of here. It looks like it's just about 2 knuckles deep on there, a little over an inch of material covering a 5-gallon bucket. Plus, if we look behind us here, we have a little bit more. I had a problem with the hose stopping up, and I began just discharging it on the ground. So here's a bit more, not a whole lot more, of material that was taken out of it. This video clip is a little bit out of sequence. It's actually after the work has been completed. I just thought I would show you here. In order to insert the cleaning tool, I had to remove the original valve, which I'm holding in my hand. And as you see, it's made of plastic. And it took a pretty good beating. I think I used a 24-inch pipe wrench finally to get the valve out of the tank. So I didn't want to put that back, and in its place I put a galvanized steel nipple here that goes back into the tank. I think it's a 4.5-inch nipple, and on that I put a simple ball valve. This is just a PVC ball valve, and then on the discharge of the ball valve is a national pipe thread to hose bib thread, so I could hook a hose onto this and drain it in the future if I needed to. But following in the following clip, you'll see me have this cover removed over the heating element, and you'll see me remove the lower heating element using this 1.5-inch tool. You may notice it's a pretty light gauge, and considering how tight some of the other fittings are, the heating elements are usually not terribly difficult. They're not. They don't have the torque applied to them that some of the other fittings do, because they're sealed with a rubber O-ring, and so a light gauge tool like this usually works pretty nice for removing them. The reason for me to remove this heating element is that I wanted to insert an inspection camera and try to get some idea as to how good a job my cleaning tool did on cleaning the tank. So with that, we'll proceed on. Well, we've taken the lower heating element out of this unit, and after having completed the cleaning process, as you can perhaps see, getting ready to do a look inside using a scope, you see the new valve that I put in the bottom of the tank. And here is the opening where the heating element goes. There again is the end of the dip tube. So entering the tank, and that blue thing you see is the cold water fill line, which takes water in and distributes it into the bottom of the tank. Now moving in, getting a lot of reflection off the floor. The to the right slightly toward the front. And basically you see the bottom of the tank, maybe a little bit of water reflecting light off of it. Really, it looks pretty clean in this area. That dark line across there, I believe, is the seam between the side of the tank and the side wall on the bottom of the tank. Try to move around here a bit more. I believe that's just a puddle of water that I'm seeing. I'm going to pull the probe back out and I swing to the left and see how it looks on the left side of the tank. Bending the probe so it looks to the left slightly. Oh, so now we see material that has been left. I'm going to rotate the camera downward. I may just run in. Yeah, right there is the bottom of the tank, and that really doesn't give you much of an indication, but I'm going to attempt to give a little evaluation of this turbo tank cleaner and its operation. If this circle represents the water heating tank, and assume that this is the turbo cleaner here, then this device will go into the tank like so at the bottom, and the length of it is probably a little over the width of the tank, so this is designed with several kinks in it, so it has a tendency to flop around as it rotates. Also, if you'll notice, this particular area of the springs have been expanded and pulled out, and the idea is that the solids get inside the spring area, and this rotation of by the drill of the unit causes the solids to be slowly pulled back into the cutting head, which is located here, comes into the back, and then we have a hose connection here with an electric drill being on the bottom of it, rotating the whole assembly. Now, what the video seemed to show was that the cleaner favored, in this image that you see, perhaps the right side of the tank. This portion of the tank seemed to be very clean. However, the left side had at least some area here, and I couldn't really detect how big an area, a pretty much undisturbed material that it didn't pick up. Now, what could we have done to improve the operation of it? Well, perhaps if I had realized that this might be an issue, we could have temporarily rotated the drill in the reverse direction, which would cause the spring device to go to the left side of the tank, disturbing some of this material and perhaps getting it up into the floating into the liquid solution here, and the water flow in the tank would slowly push it toward the outlet here through the tool. However, when it's rotating backwards, the whatever you want to call this, almost like a conveyor that's pushing material in, will be rotating backward. It's actually going to push it upward. So you probably have to, if I wanted to use that technique, I'd have to rotate it backward for a bit, then reverse again, and hope that this material has been beaten loose, moved to the center of the tank, and then when it goes back into forward motion, then it would be pulled into the cleaner unit and exit the pipe. Now when it's in reverse, you do have a portion here that's threaded and a portion here on the back that's threaded, so you'd have to keep an eye on it since these have right-hand threads on them, to make sure that this doesn't come uncoupled for you either here or in this location. Another item to consider if you're running a gas-fired water heater is you've got a flue or a vent pipe going right up through the center. Let's say this circle represents that. And in the back of my mind, I've got to wonder whether if this one gets inserted and the rotating flailing arm here that's beating up the material, if it gets on the left side, does it only clean this area? And is it unable to, the end of it is unable to come up now to get past the flue? Now the flue will come all the way from the bottom of the tank to the top, so this would have to come up and get on this side. If it were inserted and it gets started on this side of the tank, will it only clean the right half of the tank? So I'm not sure how this will work with a gas water heater. I think it probably works much better with an electric, because you just have a big open tank. In summary, I'm really very pleased with the turbo cleaning tool. As I previously mentioned, I believe it might work better in an electric water heater than it would in a gas, because of the flue pipe that runs up through the center of the gas unit. And we didn't see it in my attempt to use the inspection camera to look inside, but I would imagine that in this area there's going to be some shading that's going to make it difficult to get. There's probably some material, I guess is what I'm trying to say, in this area, in as well as in this area. And again, if I had known, I probably would have that this would leave a pile of material on this side. I would probably have reversed it momentarily for a while, then run forward again and made an attempt to get more of the material over here. So it's a bit of a learning curve with the tool, but I must admit it's a rather clever idea, or a clever method for getting the solids out of the tank. Now there is another technique that particularly has been used with electric water heaters. The electric heating element would be above this, maybe above the drain valve, or perhaps a foot higher, inserted into the tank. And I've seen some people on YouTube who have taken out that heating element and then reached in with something like a screwdriver or some kind of a pry tool, loosened up the material in here, and then just inserted, using a shop vac, inserted inside the hole. You probably have a inch. I really didn't measure it, but probably have an inch diameter hole where this electric water heater heating element goes through, and they could actually just use a tube to suck this debris up. They'd have to stop periodically, take the tool and rod it again, and get the chunks loosened up. And sometimes the chunks were big enough it would clog. They were just using a piece of polyethylene tube, and they'd have to pull it back out and get the large chunks off. But it seemed like another approach. I'm sure also in that cleaning method there's going to be material left here and here that you just can't get your pry tool on to get it loose and then get it out where you get the vacuum, the shop vac to pick it up.
I have completed my efforts at cleaning the tank, and I have, at the present time, I have got my ammeter hooked up, and you see that it's reading a 0.88, 0.86, something like that, negative current. You see the minus sign on the side there, and that is the wrong polarity, obviously, meaning that there is a very small, well, right at the moment, say 0.71 milliamps of current in the wrong direction, meaning that a little bit of course, it's microscopic, but a bit of corrosion's going on. So now, if you'll pardon the wiggle on the camera, I'm going to plug the power supply in. Powered it up, and you see it swings to a positive current flow the way the meter is hooked up, which would indicate that the power supply should be protecting the tank. It starts out about 8 or 9 milliamps and drops down, and usually after, I've watched this a little bit, usually after a few minutes it'll settle down to around 5 milliamps of current, which is very close to the level that we had before we started the cleaning operation. I'm encouraged by that. I'm a little concerned about whether the flopping of this cleaning device inside would expose a lot more steel, and maybe the current would go up because of the cleaning device had beat away some of the glass lining in the bottom of the tank. I mean, this is not absolute proof, but the fact that the current is in the same neighborhood as it was before we started the cleaning operation, I take that as an encouraging situation.
Well, if I may, I'd like to just share a couple of final thoughts here. I scribbled down a couple of things that I want to chat with you about. I guess you noticed my surprise at the apparent good condition of the magnesium anode after such a long service period. I mean, almost 12 years. I was also surprised at the relatively small amount of solids that I found in the bottom of this tank. In fact, you know, if I'd had X-ray vision, I might have not even done the maintenance on this, but really didn't realize the conditions until, you know, I got in and actually cleaned it. Now, this home is served by a well, a deep well, and the water is drawn through limestone rock structure, so the water tends to have a lot of dissolved material and a lot of calcium type products in it. Now, perhaps, since there's only, during the time that this water heater was in service, there was only two of us, two adults living in this house, and we just use a whole lot less hot water, let's say, than, you know, a typical family with 3 or 4 kids. Also, I operate this water heater at 120 degrees, which is temperature that's fairly safe from standpoint of being scalded. It also reduces the heat loss through the wall during the idle periods. The lower the temperature of the water inside the tank, the less loss you have into the space. Well, since the solids collect on the surface of the heating element, in other words, they're dissolved in the water, they encounter the high temperature heating element, and then they tend to come out of solution and deposit on the heating element. The fact that I was running at a relatively low temperature, 120 degrees, comfortable but low, it may mean that less solids were precipitated out of the water than, let's say, if I'd had the thermostatic control set at maybe 140 or 150 degrees. Now, this unit's predecessor, as I recall, near the end of its life, it had a failed lower heating element, and that heating element was covered with solids. The tank was, the water heater, when I say the tank, was removed from this closet, taken outside, and through a rather laborious effort, I fished most of the solids out through the hole where the lower water heater element went into it. It was pretty laborious, and frankly, I pretty much decided I wouldn't do it again. I did attempt to remove the heating element from that unit, or excuse me, the anode from that unit, and I was never really able to get that anode out. Now, that was all due to the fact that I had not come up with a good way to tie the tank down to keep it from rotating, and at that time I didn't have available a impact wrench, so I just decided to move ahead, put the unit back together. It seemed to work just fine. However, a couple of years later, the tank did develop a leak, and so that was when that tank was retired with this new Whirlpool unit. Now, I'm not against regular maintenance of equipment to try to extend its life, but frankly, water heater maintenance as described in the owner's manual is kind of a joke. To flush solids out of the tank, it's almost impossible because of this little valve that they have here. The opening is so small. If you've got any floating solids in there, it's going to clog up even if you've got it wide open. Why they don't use a full-throated, let's say a full-throated ball valve, I don't know, but flushing solids is just out of whack. And in other water heaters that I've encountered, when I did open this valve and maybe ran a wire back up there and tried to flush solids out, there was a tendency for the solids or the grit to get into the valve seat. And at least in one case, I remember having a heck of a time ever getting this valve to seat after it had been, or to stop leaking, let's say, when it was closed. So I just pretty much had written off regular flushing of the tank as being kind of a stupid idea. However, recently I had seen a couple of YouTube videos where servicing a tank with the right equipment did not seem to be that big a deal. For instance, one important factor is to use an impact wrench to remove the anode. Now, I know that in this room it's probably not 5 feet across for this little mechanical room where I'm standing. And I'm probably going to need, if I just used a wrench and tried to torque it by hand, I'd probably need a 5 or 6 foot long pipe on the end of my breakover bar in order to develop enough torque. And then I'd probably need a second person or persons to help stabilize this tank by putting a belt around it or something to keep it from rotating. And that's just a real bear. Usually I'm working by myself, so it's just not practical. The other thing was the idea of the turbo tank cleaner. It seems like it's a fairly neat process for removing the solids. And then also I think I might have mentioned I have seen a video where a shop vac with a piece of clear poly pipe was inserted through the hole for the water heater element, and just used a shop vac to, once the material was broken loose with some sort of a pry tool, it would slowly vacuum the material out. But I haven't tried that out. I don't know how well it works. Now, one thing that I think that I need to kind of suggest is, if you're thinking of doing this yourself and you're new to this, you might want to start early in the day, because in order to use the turbo cleaning tool, you need to take out this existing valve. And a lot of the water heaters, as this one did, uses these plastic valves. Occasionally, when you try to torque this valve, it will break. And that can turn a project that should take an hour and a half, you may shoot a whole day messing with it, trying to get the end of this valve out of here. It's just one of the features a little bit irritating. So if you get this valve out, and thankfully there was no real problem here other than I kind of messed the valve up. I had to use a pipe wrench. But once you get the valve out, I would certainly suggest, and I think I've shown that earlier in the video here, that you don't put this plastic valve back in place. Replace it with a piece of galvanized steel pipe and a valve that you can easily get to and replace, and one with a full-size, full-throated orifice through it, so that you can, if you have to run a rod through it to get it unclogged for some reason, you're able to do that. Well, I want to thank you all for watching my efforts on this. Thank you for watching. Hope that you have something here that will be useful for you. And until next time, I'll say goodbye.